Hello friends, myself Dr. Nandakumar Raubawale from College of Engineering Ambadugai is going to deal with Applied Thermodynamics 2. This is our second lecture. In previous lecture we have discussed about definition of refrigeration, then applications of refrigeration, unit of refrigeration, coefficient of performance, definition of coefficient of performance, refrigeration load, systems of refrigeration, and today we are going to discuss about coefficient of performance of heat engine, coefficient of performance of a refrigerator, coefficient of performance of a heat pump, then sources of cooling load, air refrigeration system, advantages of air refrigeration, disadvantages of air refrigeration, and working of air refrigeration cycle on reversed Carnot cycle. So now, so what this heat engine is, that we will see. So generally, according to the second law of thermodynamics, Kelvin-Planck statement is given. That is nothing but a heat engine is nothing but a power producing machine where the heat energy is consumed and produces mechanical work by rejecting the heat to the lower temperature reservoir at a lower temperature. So generally when a heat engine works, so heat energy is absorbed by heat engine from a body at higher temperature, and this converts this heat energy into work, and remaining of the heat energy is rejected to the body at lower temperature, from higher temperature to the lower temperature. So this is the working principle of engine. So now how this definition is given. So what this Kelvin-Planck statement says, it is impossible to construct a device. So he says that the device cannot be constructed that operates continuously in a cycle. A device which is operating in continuously in cycle and which produces no effect other than the removal of heat energy from a single reservoir and converts all heat energy into useful work. That means what he says, if there is a reservoir at higher temperature and if a machine absorbs heat energy from this reservoir at higher temperature, and that heat energy, Q1 heat energy, is taken from this, and say for example this is engine and it is producing work, so there is no heat rejected, Q2 is equal to 0. So it is impossible to convert almost all heat energy which is absorbed by a machine into work without rejecting heat energy. That means it is impossible to develop such a machine which will produce a work without rejecting heat energy to the body at a lower temperature. That indirectly tells us that the device which is not rejecting heat energy is converting almost all heat energy entering into it into the work is impossible. Indirectly he says that it is possible to have the machine which absorbs heat energy from a body at higher temperature and produces work by rejecting some sort of heat energy to the body at lower temperature. This is possible, whereas this is not possible. So Q2 has to be rejected, then only the work can be produced. That is nothing but 100% heat energy Q1 which is absorbed cannot be converted into work, but it is possible that Q1 amount of heat energy is absorbed and that is converted into work and some part of heat energy is rejected. So this is possible. So indirectly what he says, it is impossible to construct a device that operates continuously in a cycle and produces no effect other than removal of heat energy from a single reservoir and converts all heat into useful work. So whatever amount of heat energy it absorbs, that is converted into work. Such a machine is not possible to be produced. But indirectly he says that the machine which absorbs heat energy from a body at a higher temperature and produces work, some part of heat energy is rejected to a body at lower temperature. Indirectly he says that 100% heat energy cannot be converted into work. Some sort of heat energy has to be rejected. So this is the second law of thermodynamics. According to second law of thermodynamics, the Kelvin-Planck statement says that it is impossible to develop a machine which produces continuous work, thereby in exchanging heat with a single reservoir. Single reservoir means whatever amount of heat energy it absorbs cannot be converted 100% into work. In other way, it says that it is possible to develop a machine which will convert part of heat energy into work and part of heat energy is rejected to the body at lower temperature. And second one, so this heat engine has got a body at higher temperature we call as a source. This is called as a source, and this is a sink, say. So here Q1 amount of heat energy is taken by this heat engine from a reservoir at higher temperature, that is source, and work is developed. Some part of heat energy is converted into work and some part of heat energy is rejected to the reservoir at lower temperature. We call it as a sink. So here the temperature of source is higher than the temperature of reservoir. So Carnot efficiency is given by the work produced. What is the output? So amount of heat given to this machine is Q1, amount of heat rejected is Q2. So Q1 minus Q2 is nothing but work produced. So out of that Q1 energy, Q2 is rejected, means amount of work done is Q1 minus Q2. Work done divided by, so input is Q1. So Carnot efficiency is nothing but Q1 minus Q2 divided by Q1, or this Carnot efficiency is given by T1 minus T2 divided by T1, where T1 is the temperature of source, whereas T2 is the temperature of sink. So sink means a body at lower temperature and source is nothing but a body at higher temperature. Now I will move to this refrigerator. What is this refrigerator? What is difference between heat pump and heat engine and refrigerator? So according to second law of thermodynamics, that is the Clausius statement, what it says, it is impossible to construct a device. Again it says that it is impossible to construct a device or machine that operates in a cycle. It operates in a cycle, produces no effect other than transfer of heat. Produces no effect other than transfer of heat from a body at lower temperature to a body at higher temperature without any external aid. Without any external aid. So that what it is saying that say for example there is a refrigerator and which absorbs heat energy from a body at a lower temperature, and this amount of heat energy which is absorbed is Q1, say, and this heat energy is transferred by this refrigerator to a body at higher temperature, say TH, and it rejects this amount of heat energy Q1 to the body at higher temperature without aid of any kind of energy, without any external energy. So this is a machine which is going to transfer heat energy from a body at lower temperature to a body at higher temperature without any external aid. That means without consuming any kind of other energy, it is transferring heat energy from a body at lower temperature to body at higher temperature. So is it possible to transfer heat energy from body at lower temperature to the body at higher temperature? Never. So it is not possible to transfer water from a lower level to the higher level without aid of any kind of energy. It is impossible. But it is possible to transfer water from a lower altitude to the location at higher altitude with the help of a pump. Pump can supply water from a lower altitude to the higher altitude, and this pump consumes the work energy or electrical energy. So that is possible. But what is not possible? It is not possible to transfer water from a lower altitude to the higher altitude. In the same way, it is not possible for us to transfer heat energy from a body at lower temperature to a body at higher temperature without aid of external energy. That is nothing but indirectly second law of thermodynamics or Clausius statement says that heat energy can be transferred from a low body at lower temperature to a body at higher temperature with the aid of work. So if we supply work to this system or this machine can transfer heat energy from a body at lower temperature to a body at higher temperature. It is possible. So this is Q2 amount of heat energy is rejected. So this statement is saying that it is impossible to transfer heat energy from a body at lower temperature to a body at higher temperature without aid of any kind of energy. So now we can reread this statement. It is impossible to construct a device that operates in a cycle and produces no effect other than transfer of heat. Produces no effect other than the transfer of heat energy from a body at lower temperature to a body at higher temperature without any external aid, without using any kind of energy. That is impossible. That means it is possible to transfer heat energy from a body at lower temperature to a body at higher temperature with the aid of external source of energy. So now this refrigerator, now what this refrigerator does, that we will see. So here this is the space which has to be maintained at a lower temperature than surrounding. To maintain this space colder than the surrounding temperature or atmospheric temperature. So Q2 amount of heat energy is absorbed by this refrigerator with the help of this work input, and this energy is transferred to the body at higher temperature. That is nothing but it is rejected to the atmosphere. So Q1 amount of heat is rejected, Q2 amount of heat is absorbed. Now we can see COP of a refrigerator is defined as desired effect, ratio of desired effect to work input. So what is desired effect? So what is desired effect is nothing but our aim in this refrigerator is to maintain this body at lower temperature. So therefore we start to absorb Q2 amount of heat energy. So this Q2 amount of heat energy which is removed from this body at lower temperature is nothing but desired effect. Our aim is to remove Q2 amount of heat energy from a body at lower temperature. So this is our desired effect. Now this is desired effect divided by work supplied. So this work supplied to this refrigerator which transfers heat energy from a body at lower temperature to a body at higher temperature. So this ratio is nothing but the coefficient of performance of a refrigerator. So work done. Now here work done, net work done is nothing but Q1 amount of heat energy is rejected, Q2 amount of heat energy is absorbed. So net work done required is Q1 minus Q2. So here amount of energy rejected is Q1 plus W. So here Q1 plus W is rejected and Q2 is absorbed. So in other way we can say that net work required is Q1 minus Q2. So how much of work is absorbed here is say this is Q1 is equal to W plus Q2. So amount of energy which is rejected to the atmosphere is addition of heat energy absorbed by this machine from a body at lower temperature and energy supplied in the form of work. So these two energies add together and form the amount of heat energy which is rejected, that is Q1. Q1 is nothing but sum of amount of work energy as well as amount of heat energy absorbed from a body at lower temperature. So this is net work done is nothing but Q1 minus Q2. So here COP is defined as desired effect is Q2 as we have defined, and net work input is Q1 minus Q2. So this is nothing but COP of a refrigerator. So Q2 is amount of heat absorbed, Q1 is the amount of heat rejected. So from this we get COP of a refrigerator. Now what is aim of this refrigerator is to maintain this space below the temperature of surrounding or atmospheric temperature, say. Now what is heat pump? So now this heat pump is similar to this what you say refrigerator, but aim is different. So in previous case we were interested to maintain a body which is at lower temperature than the surrounding, but here in heat pump our aim is to maintain this temperature of hot body above the atmospheric temperature. So here heat is supplied to this. In previous case, in case of refrigerator, heat is absorbed. This Q2 was our desired effect. Now here our desired effect is Q1. So we want to supply continuously heat energy to this space so that the temperature of space will be maintained above the surrounding temperature. So here in case of heat pump, aim is to maintain higher temperature of this space above the atmospheric. In case of refrigerator, aim is to maintain temperature of lower body lower than the temperature of body lower than the atmospheric temperature. So aim is different. So desired effect in case of refrigerator is Q2, desired effect in case of heat pump is Q1. So now this desired effect is Q1 now. So now again heat energy is taken from atmosphere or surrounding which is at lower temperature than the room. So heat is supplied continuously to this room in order to maintain temperature of room above atmospheric temperature. So here desired effect is Q1 and in work input is W. So now COP of heat pump is defined as a desired effect to the work input. Now definition of desired effect is going to change. In previous case desired effect was Q2, now here desired effect is Q1 because we want to maintain this body or this room above the atmospheric temperature. So in case of refrigerator our aim was to maintain this space below the atmospheric temperature. So now we can see desired effect is Q1. So net work done is nothing but addition Q1 is equal to W plus Q2. So or W is equal to Q1 minus Q2. So here Q1 we can say Q1 is equal to W plus Q2 or W is equal to Q1 minus Q2. So amount of heat energy rejected is nothing but sum of work done plus heat energy absorbed from a body at lower temperature. So now this is written as Q1 is equal to Q2 plus W. Now COP of heat pump is given as desired effect is Q1 now, Q1 divided by Q1 minus Q2. So now COP of heat pump can be written as Q1 is equal to Q2 plus W. So in place of Q1 we are substituting Q2 plus W divided by Q1 minus Q2, denominator is as it is. On simplification, just we divide Q1 minus Q2 with this Q2, Q2 divided by Q1 minus Q2 plus W divided by Q1 minus Q2. So if we see this Q2 divided by Q1 minus Q2 is COP of this is COP of a refrigerator. This Q2 divided by Q1 minus Q2 is COP of refrigerator, whereas this becomes equal to 1. How this becomes equal to 1? So we can see here W is equal to Q1 minus Q2. So if we substitute W as Q1 minus Q2, Q1 minus Q2 in numerator and Q1 minus Q2 in denominator gets cancelled and this term becomes 1. So this first term is nothing but COP of a refrigerator, second term is 1. So we can write this COP is equal to COP of heat pump is equal to COP of refrigerator plus W divided by Q1 minus Q2. So COP of refrigerator is COP of heat pump is equal to COP of refrigerator plus 1. So this term this term becomes COP of refrigerator, and second term becomes this W divided by Q1 minus Q2 becomes 1, because this W is nothing but Q1 minus Q2. Q1 minus Q2, Q1 minus Q2 gets cancelled. So what we can conclude is COP of heat pump is equal to COP of refrigerator plus 1. Always COP of heat pump is greater than COP of refrigerator by 1. So this is conclusion here, and aim of heat pump is to maintain the body at higher temperature than the surrounding, whereas aim of refrigerator is to maintain body at lower temperature than the surrounding. So aim changes, therefore desired effect also changes. In case of refrigerator Q2 is the desired effect, and in case of heat pump Q1 is the desired effect, but the working principle is same. So refrigeration load. So what is refrigeration load? So already we have seen the rate at which heat energy enters into refrigerated space. Say for example, you have a refrigerator at your home. So generally this refrigerator runs continuously. Why this runs continuously? Because the heat energy always enters from surrounding into the refrigerator, because there is a temperature difference. So due to the temperature difference, heat energy from surrounding always enters into the body or into the refrigerator. So amount of heat energy which always enters into this refrigerator has to be removed. So the removal of that heat energy is necessary. Therefore the heat energy which enters into the refrigerator continuously because of temperature gradient, because of opening of the door, or maybe any other reason, so that amount of heat energy which enters into the refrigerator and that has to be removed continuously is known as the refrigeration load. So here it is defined as a rate at which heat enters into the refrigerated space, which has to be removed in order to maintain desired temperature of space, is known as a refrigeration load. So from where this refrigeration load comes? So from where heat energy enters into the refrigerated space. So heat gained by conduction through wall. So if this is a refrigerator, heat energy enters from walls by the mode of conduction. And second one, heat gain from radiation through transparent material. Sometimes through transparent materials. So here sometimes some of the refrigerators are using some glass covers, or door is made of glass. So the heat energy enters into the refrigerator because of radiation, by the process of radiation or mode of radiation. The next one is heat emitted by products kept inside the space. Say for example, germinating seeds, if you are going to keep inside the refrigerator, germinating seeds always tend to liberate heat energy. So that heat energy liberated also adds into the cooling load of refrigerator. So anything that you are going to keep, say for example hot milk you are going to keep into the refrigerator, so that hot milk is going to emit heat energy into the refrigerator, so that adds into the cooling load. Heat emitted by occupants. So if you are going to keep any grains or something which is hot, and then that emits some heat energy into the refrigerator, or if it is being used in case of air conditioning. So if human being is many of people are going to sit into the air conditioned room, so if these people are sitting into the air conditioned room, always human body emits the heat energy. So number of occupants in the refrigerated space or in a air conditioned space are going to emit heat. So heat emitted by occupants is one of the source of cooling load. Heat emitted by heat generating equipment. Say for example, when you are dealing with air conditioning system, so air conditioning is made to the room. So in that room there will be a lamp, there will be a fan, there will be a refrigerator, there may be a television. So many devices are working into the air conditioned space. So such devices are going to emit heat energy, and that adds to the cooling load. Then air refrigeration system. So what is this air refrigeration system? The refrigeration system that uses air as working substance is known as a air refrigeration system. So what is working substance? It is a medium which transfers heat energy from one location to another location. So it is a medium through which heat energy is transferred. So if air is used to transfer heat energy from one location to the another location, then that air is known as a working substance. If air is used as a working substance, then that kind of refrigeration system is known as a air refrigeration system. Then heat carrying capacity of air per unit mass of air is very small compared to other refrigerants. So heat carrying capacity, specific heat, we call it as a specific heat. Specific heat is very low. Therefore, if the specific heat of air is low compared with the other refrigerants, so here vapor compression refrigeration is using some other refrigerants, not air. So the heat carrying capacity is more. Therefore, in that case, the mass of refrigerant required is less. But here in case of air refrigeration system, mass of air required is more in order to carry same quantity of heat energy. So heat carrying capacity is less. Then to produce desired refrigerating effect, large amount of air is required, because air has got small heat carrying capacity. Therefore, the system requires large quantity of air, and to carry or to deal with large quantity of air, so compressor and heat exchanger required are of larger size. So this is one of the disadvantage. Then in aircraft, say in aircraft, this air refrigeration system is preferred, because the rammed air means when the aeroplane or aircraft moves in the forward direction, in opposite direction air hits to this aircraft, and this air which hits to this aircraft is getting compressed, and that compressed air is used in order to produce refrigerating effect or air conditioning of this aircraft. So this compressed air which is produced because of ramming effect. So as this aircraft moves at a very high velocity, so it hits with the air, and this air which hits to this aircraft gets compressed, and that compressed air is used for developing the air conditioning effect in a aircraft. So there this compressed air is used for air conditioning of aircraft. So now advantages of air refrigeration. So refrigerant is cheap because air is freely available. This is one of the advantage. Second one, available in large quantity. So air is available in large quantity. Then safe to use because it is not flammable, it is not harmful, it is not what you say pollutant. So it is safe to use. Then easy for maintenance and repairs. If you want to do maintenance of such a refrigeration system, and if there is a leakage, so if air leaks out, it doesn't matter, it does not cost a lot. So therefore easy maintenance and repair can be made for a system using air as a refrigerant. Then pollution free. So such a refrigerant is pollution free, and charging of refrigerant is simple and free of cost, because this refrigerant is available in atmosphere, and that can be used freely without paying any cost for charging of that refrigerant. So what are the disadvantages of air refrigeration? Needs larger compressor of larger capacity. Then energy consumption is more, because when we are using compressor of larger capacity, this requires a lot of energy to compress this air. So energy consumption of larger compressor is more. Then condenser and evaporator to be of larger size and capacity. Again, along with this, we need to use condenser and evaporator in a refrigeration system which will be of larger size and larger capacity. Then this air refrigeration is nowadays being preferred, because this compressors which are of rotary in nature are developed, and these rotary compressors are coupled with the gas turbines, and in combination of this gas turbine and rotary compressor, so air refrigeration system proves to be economical, and therefore this air refrigeration system is nowadays going to be developed, or inventions are going to happen in this field because of development of rotary compressors. So now air refrigeration working on reversed Carnot cycle. How this air refrigeration works? So now here we see air refrigeration working on Carnot cycle. Let us consider the air taken at state 1, which is having temperature T1, volume V1 and pressure P1. So this air is compressed isentropically, that is nothing but adiabatically. So there is no transfer of heat energy, that is change in entropy is 0. So the isentropic compression process is shown here on PV diagram. Same process is shown on TS diagram. So the air at temperature T1, pressure P1, volume V1 is compressed from state 1 to state 2 adiabatically. Adiabatic process is shown by a vertical line on TS diagram. So at point 2, temperature reaches to T2, pressure reaches to P2, volume reaches to P2. So here volume is going to get reduced and pressure is going to increase from P1 to P2, temperature increases from T1 to T2, and volume reduces from V1 to V2. So during this isentropic compression, temperature of air increases from T1 to T2. And further from point 2 to 3, air is compressed by isothermal compression, reversible isothermal compression. So during which temperature is remaining constant, that is nothing but always when we are going to compress air, the temperature of air has to increase. But here this is the isothermal compression where heat energy is rejected from this system to surrounding. As the heat energy is rejected, so QR we can say heat energy is rejected from this air because of isothermal compression. The isothermal process is nothing but a constant temperature process. So this temperature changes from T1, T2 to T3, where T2 is equal to T3. T2 is equal to T3 and heat energy is rejected. So isothermal process is nothing but PV is equal to constant. Again, the pressure reaches to P3, temperature reaches to T3, volume reaches to V3. Then here heat is rejected to the surrounding, and then after this from point 3 to 4, this air is expanded isentropically. So there is no heat transfer. ds is equal to 0. So this is represented by this line 3 to 4 on TS diagram. A vertical line indicates the isentropic process. So this during isentropic expansion, pressure falls to P4, temperature falls to P4, and volume increases to V4. So here again this is isentropic process, PV raised to gamma is equal to constant, and after point 4 this air is expanded isothermally. So when air is expanded isothermally, definitely when during a expansion process, temperature of air has to fall. So here, as this is isothermal process, temperature at point 4 is equal to temperature at point 1. So it is constant temperature process, PV is equal to constant. So therefore heat energy is absorbed. So heat is rejected, heat is absorbed. So heat energy is taken. That is nothing but during process 2 to 3 heat is rejected, and during process 4 to 1 heat is supplied. So heat supplied, heat rejected. So this is nothing but heat absorbed is nothing but a desired effect, we can say, amount of heat energy taken from a body at lower temperature, and this amount of heat energy supplied to the surrounding or rejected to the surrounding, this is amount of heat rejected. So now we will see the processes one by one. Process 1 to 2. Process 1 to 2 is reversible adiabatic compression process. So air is compressed from initial pressure P1 to pressure P2, P1 to P2, till temperature of air rises from T1 to T2 in a reversible adiabatic process. So there is no heat transfer. Adiabatic process means ds is equal to 0. That process is shown on this TS diagram by a vertical line. Then second is 2 to 3 reversible isothermal process. So process 2 to 3 is reversible isothermal process. So during which air is compressed isothermally till its pressure rises from P2 to P3 at constant temperature. So temperature on this is T is equal to constant. That is nothing but temperature T2 is equal to temperature T3. T2 is equal to T3. Now during this process heat is rejected. Just we have seen QR we have written, that is QR is nothing but Q2 amount of heat rejected. During this process heat Q2 kilojoules per kg is rejected to surrounding. So amount of heat which is rejected is given by this TS diagram. So heat rejected is given by the area 2356. So heat rejected is given by 2356. If we calculate this area on this TS diagram, this area below this straight line 2 3 gives us heat rejected. So this area can be given as rectangle. Area of rectangle is height into width. So therefore T2 is the temperature at point 2. So T2 is equal to T3. So this distance we can call as a T2, and S2 minus S3. So entropy at point 2 minus entropy at point 3 is nothing but this distance. So this distance from point 2 to 3 is T2 minus S2 minus S3. So this gives us heat rejected. So in other words, T2 Q2 is equal to T2 as it is, S2 is equal to S1. We can see here entropy at point 2 is equal to entropy at point 1. S2 is equal to S1. We can say S1 is equal to S2. Entropy at point 2 is equal to entropy at point 1. So in place of S2 we write S1, in place of S3 we write S4. Entropy at point 3 is equal to entropy at point 4. So S3 is equal to S4. So this is nothing but amount of heat rejected. So heat is rejected from system to surrounding. Now we see next process 3 to 4 reversible adiabatic process. So this process 3 to 4 is reversible adiabatic process. Heat is air is expanded adiabatically. That is nothing but rate of heat transfer or change in entropy is 0. So the reversible adiabatic expansion of air takes place till pressure changes from P3 to P4 and volume changes from V3 to V4. During the process temperature falls from T3 to T4. So this is the process. Now after that last process is reversible isothermal expansion process. So this 4 to 1 is reversible isothermal expansion. During this process the pressure falls from P4 to P1, volume falls from V4 to V1 at constant temperature. T4 is equal to T1. So temperature at point 4 is equal to temperature at point 1, that is T4 is equal to T1. So here amount of heat energy, as this system is at lower temperature, so it has got affinity to absorb heat energy. So heat is absorbed, or we can call this as Q1 amount of heat is taken here. So here during this process Q1 kilojoules of heat is absorbed. So heat rejected is given by the area. So area below this line 1 to 4. So this area gives us amount of heat absorbed, or we can call this as a desired effect. So desired effect is nothing but amount of heat rejected from body at a lower temperature. So this area can be obtained. So this is the temperature, say T1. Distance is this distance, vertical distance from 4 to 5 we can call as a T1. So this is T1 and width is S2 minus S1 minus S4. So here Q1 amount of heat rejected or amount of heat absorbed is nothing but not rejected, it is absorbed. This Q1 is equal to T1. Height of this rectangle is T1. This distance is T1. Whereas S1 minus S4, S1 minus S4 is width of this rectangle. This gives us amount of heat energy rejected, sorry, absorbed. Now we'll see this net work done. The net work done during the cycle is obtained by subtracting equation number 2 from 1. So this is equation number 2 and this is equation number 1. Now we know equation number 1, we know equation number 2. This is equation number 2. The net work done during the cycle is obtained by subtracting equation 2 from equation 1. So work done is equal to Q2 minus Q1. So Q2 is nothing but T2 into S1 minus S4 minus of Q1 is nothing but T1 into S1 minus S4. So S1 minus S4 is common. We can write this as T2 minus T1 into S1 minus S4. So this is about the work done. Now we know work done. The coefficient of performance COP of Carnot refrigerator that is COP of refrigerator is equal to a refrigerating effect that is nothing but Q1 in this case divided by net work done. That is W. So we know Q1 in this case is P1 into S1 minus S4 whole divided by T2 minus of T1, work done is given by T2 minus T1 into S1 minus S4. So S1 minus S4, S1 minus S4 gets cancelled. So remains T1 divided by T2 minus T1 is COP of refrigerator working on a reverse Carnot cycle. Now if we want to find out COP of a heat pump, say for example not a refrigerator, so instead of that air heat pump we can call. If we want to find out COP of heat pump is equal to desired effect that is ultimate amount of heat energy rejected or added to the space Q2 divided by work input W. So this works out. Desired effect here is T2 into S1 minus S4 divided by T2 minus T1 into S1 minus S4. S1 minus S4, S1 minus S4 gets cancelled. So COP of heat pump is T2 divided by T2 minus T1. COP of heat pump is T2 divided by T2 minus T1, where T2 is the temperature of a body at lower temperature and T1 is the temperature of body T2 is the temperature of body at higher temperature, T1 is the temperature of body which is at lower temperature. So this is COP of heat pump. So in this way we have seen how to find out COP of heat pump refrigerator working on a reversed Carnot cycle, and that too it is using air as a working substance or a refrigerant. So we stop here. In next lecture we will discuss about other mechanisms, other cycles which are used for producing refrigerating effect. Thank you.